Welcome to G Fun Facts Online. The moment a photon from the sun collides with a solar cell, a microscopic race against time begins. For decades, the global transition to renewable energy has rested on our ability to harvest these arriving packets of light and convert them into a steady flow of electrical current. Yet, zooming into the atomic scale reveals that this conversion process is far from guaranteed. It is governed by a fragile, ephemeral phenomenon that exists precisely at the boundary between classical thermodynamics and the mind-bending realities of quantum mechanics. At the heart of this process lies a mechanism so incredibly rapid that it defies conventional chemistry, a process known as ultrafast charge separation. To understand why solar technology is currently undergoing a theoretical and practical revolution, we must journey into the sub-picosecond realm, a domain where electrons behave like waves, where the background vibrations of a molecule act as a catapult, and where the classic rules of particle physics are completely subverted. Welcome to the quantum mechanics of next-generation solar cells. Let us start with the birth of the exciton and the recombination trap. When a semiconductor material absorbs a photon, the energy of that light excites an electron, promoting it from a lower energy level, known as the valence band, to a higher energy level, the conduction band. In traditional, highly crystalline materials like silicon, the newly excited electron and the positively charged empty space it left behind, called a hole, are loosely bound and easily separate to wander through the material. This creates the electrical current that powers everything from your handheld calculator to massive city power grids. However, silicon is thick, rigid, and incredibly energy-intensive to produce. The holy grail of modern photovoltaics lies in emerging next-generation materials. We are talking about organic polymers, hybrid organic-inorganic perovskites, and atomically thin, two-dimensional transition metal dichalcogenides. These materials are flexible, tunable, and can literally be printed like ink from a solvent onto giant plastic rolls. But they come with a profound energetic catch. In these advanced materials, the dielectric constant, which is a measure of a substance's ability to screen electrical forces, is relatively low. When a photon strikes an organic solar cell, the excited electron and the hole do not immediately separate. Instead, their mutual electrostatic attraction fiercely binds them together into a single, localized quasi-particle known as an exciton. Think of an exciton as an orbiting pair of dancers, holding tightly onto one another. The binding energy of this pair is often much larger than the ambient thermal energy available at room temperature. For a solar cell to actually function and give us electricity, this exciton must be violently torn apart into free charge carriers, an electron and a hole that can travel in opposite directions to opposite electrodes. If they fail to separate, the dancers eventually tire out, recombining and releasing their stored energy as useless heat or a stray flash of luminescence. This phenomenon, known as geminate recombination, is the ultimate enemy of solar efficiency. To overcome this, engineers traditionally combine two different materials, an electron donor and an electron acceptor, creating what is called a heterojunction. The basic idea is that the energy offset between the two materials provides the driving force to rip the exciton apart. According to classical theories of chemical physics, such as Marcus theory, this charge transfer was expected to be a somewhat sluggish, incoherent process. The exciton would randomly diffuse through the material until it bumped into the boundary between the donor and acceptor, at which point the electron would hop over the barrier in a matter of picoseconds, which are trillionths of a second. But when modern researchers pointed their ultrafast lasers at highly efficient organic and perovskite solar cells, they observed something that left them completely baffled. The charges were not taking picoseconds to separate. They were separating in 10 to 100 femtoseconds. A femtosecond is 1/millionth of 1/billionth of a second. To truly put that into perspective, a single femtosecond is to 1 second what 1 second is to roughly 31.7 million years. At this incomprehensible timescale, the electron is moving so fast that classical hopping mechanisms cannot possibly account for it. The laws of classical physics completely break down, and the bizarre, probabilistic world of quantum mechanics takes over. This brings us to the breakdown of the Bohr-Oppenheimer approximation. For nearly a century, chemists and physicists have relied on a foundational rule known as the Bohr-Oppenheimer approximation. Because atomic nuclei are thousands of times heavier than electrons, this approximation assumes that electrons adjust to their environments instantaneously relative to the sluggish, heavy movements of the nuclei. In this classical view, electronic transitions and nuclear vibrations are treated as entirely separate events that do not interact. Ultrafast charge separation completely shatters this assumption. In the high-stakes environment of an organic photovoltaic blend, or a two-dimensional nanomaterial, the transfer of an electron is perfectly synchronized with the microscopic vibrations of the atomic lattice. The electronic states and the nuclear motions become inexorably intertwined, a phenomenon known in advanced physics as vibronic coupling. Recent breakthroughs have unveiled exactly how critical these vibrations are. In a landmark 2026 study published in Nature Communications, researchers observed charge separation happening in a staggering 18 femtoseconds. By utilizing laser pulses lasting less than 12 femtoseconds, the team managed to track the exact pathway of the electron. They discovered that the electron was not drifting through the material at all. Rather, specific high-frequency vibrations in the polymer backbone were mixing the electronic states at the donor-acceptor boundary. Imagine the atomic backbone of the polymer as a tightly coiled spring. As the photon strikes, the resulting burst of energy causes the carbon bonds to stretch and compress rapidly. These specific tuning and coupling modes force the potential energy surfaces of the donor and acceptor to intersect, creating a massive quantum funnel known as a conical intersection. Through this intersection, the vibronic motion literally catapults the electron across the interface in one coherent, instantaneous burst. The vibrations act as a structural bridge, allowing the electron to entirely bypass the thermodynamic barriers that would otherwise impede its journey. This non-adiabatic dynamics completely changes how we view solar energy conversion. It demonstrates that the ultimate speed limit of charge separation is not dictated merely by static energy levels, but by the dynamic, rhythmic breathing of the molecules themselves. But the molecular catapult is only part of the puzzle. Once the excitant reaches the interface, how does the electron physically cross it so efficiently without instantly bouncing back? The answer lies in quantum coherence, essentially riding the probability wave. In our normal macroscopic world, an object occupies a single defined space. You are either in your chair or you are not. But in the quantum realm, particles like electrons can exist as a superposition of probabilities, meaning they act as a wave extending across multiple physical locations all at once. Quantum coherence refers to the maintenance of this delicate wave-like state before interactions with the chaotic, messy, warm environment cause it to collapse back into a normal classical particle. For a very long time, scientists firmly believed that quantum coherence could only exist in highly controlled, ultra-cold laboratory vacuums isolated from the outside world. The idea that a fragile quantum wave could survive in a warm, vibrating, highly disordered solar cell sitting on a hot roof at room temperature seemed completely absurd. Yet, life itself provided the first massive clue. In natural photosynthesis, biological structures such as the Finna-Matthews-Olsen complex utilize exact quantum coherence to route solar energy to reaction centers with near-perfect efficiency. Plants and bacteria mastered quantum mechanics billions of years before we even knew it existed. Drawing inspiration from nature, researchers began examining artificial light harvesting systems, such as supramolecular triads made of keratin, porphyrin, and fullerene. Using high-time resolution femtosecond spectroscopy, combined with time-dependent density functional theory, they found compelling evidence that the driving mechanism of photo-induced current generation is a correlated, wave-like motion of electrons and nuclei. The interface between the light absorber and the charge acceptor actively triggers a coherent, wave-like electron hole, splitting on a timescale of just a few tens of femtoseconds. When the excitant hits the heterojunction of a modern organic solar cell, the electron does not simply jump from molecule A to molecule B like a person stepping over a puddle. Instead, its wave function undergoes rapid delocalization. The electron probability cloud smears out instantly, spreading over a vast aggregate of acceptor molecules. This delocalization acts as a brilliant quantum safety net. By instantly spreading out over a distance of 4 nanometers or more, which is incredibly far on the atomic scale, the electron moves far beyond the reach of the whole electrostatic pull. The electron completely prevents geminate recombination because the electron and hole are physically separated before the environment even has the time to realize what has happened. In cutting-edge materials like transition metal dichalcogenides, this delocalization is particularly pronounced for electrons compared to holes, resulting in longer coherence times, faster sub-picosecond transfer, and robust charge separation, despite massive electrical interactions trying to pull them back together. While quantum coherence and vibronic coupling beautifully explain the initial ultrafast burst of charge separation, the charges must remain separated long enough to travel all the way to the electrical contacts. What keeps the electron from turning around and falling back into the hole after the initial jump? Here, quantum mechanics joins forces with thermodynamics, specifically through the unstoppable power of entropy. In traditional physics, the driving force for a chemical reaction is often thought of as an energy drop, like a ball rolling down a steep hill. But the universe is also governed by entropy, the fundamental drive toward disorder and a higher number of accessible microstates. In high-performance organic solar cells, researchers have discovered that the dense density of states for long-range charge transfer acts as an entropic wedge. When the excitant dissociates, it does not just transition into one possible separated state. Thanks to the amorphous, complex aggregation of donor and acceptor molecules, the electron has access to a massive manifold of potential energetic states. Because the atomic vibrations induce a quantum resonance between the localized exciton and this broad array of long-range states, the system naturally flows toward the scenario with the most options. This entropy-increasing effect vastly lowers the free energy barrier for charge generation. Even if the energetic hill the electron must climb to truly escape the hole is relatively steep, the sheer number of possible escape routes mathematically overwhelms the energetic penalty. It is the microscopic equivalent of a prison break. If a wall is tall, but there are 10 million open doors scattered all across it, the probability of escape approaches absolute certainty. Furthermore, as the electron wave function expands into this new territory, it undergoes a process called polaron formation. As the electron settles into its new environment, the surrounding atomic lattice distorts slightly to accommodate the negative charge. This physical distortion acts as a protective, energetic shell, stabilizing the charge and preventing non-geminate recombination. This means that even if the electron and hole accidentally cross paths later during their journey to the electrodes, the probability of them recombining is significantly suppressed by this protective distortion. The true beauty of ultrafast charge separation is how profoundly it is influenced by the unique architectures of advanced nanomaterials. Each material class presents its own playground for quantum phenomena to come alive. Take organic photovoltaics, for example. In these devices, active layers are typically composed of a bulk heterojunction, which is an intimately mixed blend of polymer donors and molecular acceptors. For years, the efficiency of these devices was hindered by significant energy losses. To ensure the electrons separated from the hole, engineers felt they had to use materials with a massive energy offset. This offset acted like a waterfall, guaranteeing the electron fell away from the hole, but this came at a severe cost to the overall voltage output of the solar cell. However, armed with the new understanding of vibronic catapults and quantum coherence, researchers now realize that large static energy offsets are completely unnecessary. If the molecular vibrations of the donor and acceptor are tuned to match perfectly, vibronic coupling can drive the separation even when the energy offset is virtually zero. This revelation shatters the historic trade-off between speed and efficiency, paving the way for organic solar cells that generate very high voltages while maintaining near-unity internal quantum efficiencies. Then we have two-dimensional transition metal dichalcogenides, or TMDs. Materials like molybdenum disulfide and molybdenum diselenide offer entirely different quantum advantages. These materials are atomically thin, literally just a few atoms thick. Because they are restricted to strictly two dimensions, the Coulombic attraction between the electron and hole is unusually strong, because there is no three-dimensional space to screen the electric field. Under classical rules, one might expect charge separation at a junction between these materials to be wildly inefficient, yet experiments utterly defy this expectation. Using time-domain density functional theory and advanced molecular dynamics, researchers have found that quantum coherence facilitates rapid, sub-picosecond charge transfer across these interfaces. The transfer is heavily promoted by out-of-plane vibrational modes of the metal and chalcogen atoms. Interestingly, the physical weight of the atoms actually matters here. Lighter sulfur atoms in molybdenum disulfide create much larger coupling effects for electrons than the heavier selenium atoms in molybdenum diselenide, accelerating the electron transfer even further. The resulting hot hole relaxes slowly, enabling long-distance band-like transport and favoring an incredibly long-lived charge-separated state. And we cannot talk about next-generation materials without mentioning perovskites, the three-dimensional and two-dimensional miracle materials. Organometal halide perovskites have taken the photovoltaic world by absolute storm, soaring from single-digit efficiencies to over 25% in just a single decade. Their secret lies in their unparalleled ability to generate highly mobile charges with exceptionally slow recombination rates. When examining materials like two-dimensional cesium-lead bromide nanoplatelets, researchers using transient absorption spectroscopy note that efficient charge separation can be achieved by transferring electrons and holes to adsorbed molecular acceptors. The half-life of these charge-separated states can exceed 100 nanoseconds. That is an absolute eternity in the quantum realm, making them profoundly useful not just for solar panels, but for advanced photocatalysis and chemical manufacturing. By engineering complex heterostructures that combine the massive light-absorbing capabilities of three-dimensional perovskites with the transport properties of monolayer semiconductors, scientists have created systems where interfacial hole transfer occurs in a mind-boggling 100 femtoseconds, while electrons transfer in roughly 3 picoseconds. Because the hole rapidly diffuses away from the interface within the thick perovskite layer, the physical distance between the charges increases dramatically. This coupled long-range diffusion and ultra-fast interfacial transfer results in near-perfect efficiency. At the even smaller nanoscale, artificial atoms known as quantum dots allow for extreme control over exciton dynamics. By designing core and shell structures such as a cadmium selenide core surrounded by a cadmium sulfide shell, scientists can physically engineer the quantum tunneling barrier the electron must traverse. Femtosecond absorption spectroscopy has shown that while electrons in these structures are highly delocalized, they still must overcome a specific energetic barrier dictated by the exact thickness of the shell. By altering the crystal lattice to a fraction of an angstrom, one can dictate the exact femtosecond timing of the electron escape, highlighting how precise structural engineering translates directly into absolute quantum control. You might be wondering, how do we actually know any of this is happening? You cannot exactly put a polymer solar cell under a standard desktop microscope and watch an electron wave function collapse. The visualization of ultrafast charge separation requires some of the most sophisticated, expensive, and complex optical instrumentation on the planet. The absolute workhorse of ultrafast physical chemistry is femtosecond transient absorption spectroscopy. A highly energetic pump laser pulse is fired into the sample to excite the molecules, perfectly simulating a photon of sunlight. Mere femtoseconds later, a weaker probe pulse is fired. By measuring exactly how the sample absorption of the probe pulse changes at different incredibly tiny time delays, scientists can piece together a high-speed stop-motion movie of the electron journey. To prove the existence of the molecular catapult and vibronic coupling, scientists rely on time-domain Raman spectroscopy. These techniques utilize impulsive laser excitation to generate nuclear wave packets. By tracking the coherent evolution of these wave packets through reaction pathways, researchers can watch in real time as specific carbon-carbon stretching modes actively drive charge transfer. They can literally see the structural breathing of crystalline organic thin films and correlate that physical motion directly to the electrical current being generated. Another vital tool is time-resolved terahertz spectroscopy. Terahertz radiation is exquisitely sensitive to the motion of free charges, allowing scientists to watch polaron dynamics in real time. By measuring the complex optical conductivity of a material just picoseconds after photoexcitation, terahertz pulses map the mobility and delocalization of the charges, proving that minimizing trap states is the ultimate key to extracting these charges before they are lost. The revelation that quantum coherence, vibronic coupling, and entropic density of states govern ultrafast charge separation is not just a triumph of fundamental physics. It is a literal roadmap for the entire future of humanity energy infrastructure. For years, the development of new solar materials was largely empirical, essentially a cycle of synthesizing thousands of different chemical derivatives, blending them together, baking them, and hoping for a higher efficiency. Device engineering was heavily constrained by classical assumptions, namely, that to ensure charge separation, one had to sacrifice voltage to create a steep energetic drop. Today, those rules are being completely rewritten. If the ultimate speed of charge separation is determined by how molecules vibrate, rather than just their static electronic structures, then chemists can begin performing rational, quantum-directed material design. By using immense computing power for multi-layer quantum dynamics simulations, engineers can intentionally design polymer backbones whose high-frequency vibrations perfectly align with the electronic band gaps of their partner materials. We can mathematically design organic solar cells that separate charges in under 20 femtoseconds, without losing any excess voltage whatsoever. This paradigm shift extends far beyond rooftop solar panels. The exact same ultrafast, quantum-coherent charge separation mechanisms are the critical bottleneck in artificial photosynthesis and photocatalytic water splitting. By engineering advanced structures that leverage these quantum phenomena, we can use sunlight to directly split water into clean hydrogen fuel or suck atmospheric carbon dioxide out of the air and reduce it into usable synthetic hydrocarbons. Furthermore, an intricate command over nanoscale charge separation holds vast implications for the development of highly sensitive photodetectors, optical switches, medical bioimaging agents, and future quantum information technologies. When we stand outside in the warmth of the sun, we are experiencing the end result of a magnificent cosmic journey. A photon born in the immense fusion furnace of a star travels 93 million miles across the freezing, empty vacuum of space, only to strike a microscopic printed film of organic molecules or a delicate lattice of perovskite crystals. What happens next is nothing short of a symphony of quantum mechanics. In a fraction of a single femtosecond, the photon energy is absorbed, awakening and exciting. The molecular lattice responds instantly, its atoms vibrating in a perfectly synchronized rhythm. These vibrations bend the local energetic landscape, creating a transient, invisible bridge. The electron, shedding its identity as a distinct classical particle, spreads out into a massive wave of probability, delocalizing entirely across the molecular architecture. Driven by the entropic pull of 1,000 possible futures, the electron surges completely across the interface in less than 20 femtoseconds, leaving the whole safely behind. By the time one single second has passed on your watch, this miraculous quantum leap has occurred trillions upon trillions of times, coalescing into a steady macroscopic flow of electricity that lights up our cities. It is a process that beautifully defies the constraints of classical thermodynamics, harnessing the deepest, most mysterious laws of the quantum universe to power our modern world. And as our understanding of ultrafast charge separation continues to deepen, we move ever closer to a future where the boundless energy of the sun is captured with perfect, quantum-tuned precision. Thank you for joining us today on Fun Facts Online, where we dive into the incredible science shaping our universe.